Hello, everyone. So today I received a question from a student that I tutor, and she's wondering how do we go about solving problems like this. Now, I ended up rotating it to be able to read it well, and essentially this problem is asking about Hess law. How do we add overall reactions and go about of solving for the final reaction enthalpy change? And here we see this is our actual full reaction that we care about. Then these are the parts of it. The way they give it to us is not perfectly representative to what we have, and that's why this question seems to give students a little bit of issues at times. So let's take a look at a step-by-step way of doing this reaction. This is how I typically attack it. So first thing first I'd like to do is I would like to, well, you definitely need a sheet of paper for this. Is not something to do on the fly. So first thing I would like to write down S, the actual flow reaction, and go about. Oh, that was too big. Should probably zoom in a little bit before we start here. All right, so that we got that at about 100%. All right, so I'd like to write down my full reaction first, so I know I have something to reference to because it will help me in the long run. And I'm going to go ahead and write down the parts they gave me. Now, what they really want to know is actually, I'm going to write that down here. It's the delta H of this reaction. That would be something we're going to have to calculate through what we were given. So here I have these pieces. Uh, and we also have these other piece that they gave us. Now, as you look through this, you start to realize that the final product here that I'm about to draw does not really match what I'm trying to make. So I'm not trying to make 2SO2 plus O2 here. That's not what I'm trying to make. I'm trying to make SO3, and SO3 is here. That's right off the bat. That's an issue, right? Now we also know that in when we're doing this reaction, so for example, if you see on the left side here, we have C and C cancel. So things that are the same but are on opposite sides of the reactions that we're adding could also be canceled out. These are intermediates, and they're not. We only care about the beginning point and the end point of the reaction when calculating enthalpy change. So that right of the way signals me that okay, I have my right reactants on the right side. I do need to fix this in a minute, these coefficients and everything, but that will kind of get sorted out. That's not your first worry. First worry is are the main, I guess, element or molecule there. We don't care about the coefficient right now at the moment. But essentially, I know that this is on the right side, but this is not. So I would flip this over. Now, as you can realize, this was a positive 198 kilojoules from what we were given. You can see my cursor, it's right here. If I flip it, it's going to become negative. So I'm going to kind of carry this around. If it's carryable, it is. Bring this down. Um, then this would be right here. Beautiful. And when I flip that over, I again also would end up flipping um, my sign from positive 198 to a negative 198 kilojoules. This is not going to change right now because we did not flip it. We didn't do anything to it. It's still a negative 297 kilojoules. Cool. All right. So let's see what we have here now. I have SO2 and SO2 on opposite sides in different two reactions we're working with, and that could only signal me to the fact that I might be warranted to actually delete each of those. Now the problem is, let's say I wanted to cancel both of them out, right? I don't have the same amount of SO2 over here to cancel what's here. That's right off the bat a red flag. So what I would do is I would double this reaction. So I would have to do this reaction twice in real life to be able to move on and take enough SO2s to run the second reaction, right? To make it happen. So if I wanted to run this thing twice, so I have to have two amounts of everything. And that in turn, as you might imagine, will double my enthalpy change because of this reaction. Now I have to do this reaction twice, so I need twice the amount, and that will also, um, I guess, yield out toward the system, from the system to the surrounding, um, double the amount of energy. So I would time this number by 2. We'll take care of that in a second. So now I could actually, that would, let me do that on my calculator here. 297 times 2, and the answer would be negative. That would be a negative 594, and the units would not change, as you might imagine. So that we have done that now. Now let's start crossing things out. Now I know I could cross these out. They have the same number. They're the same thing. They're gone. Um, Eventually, they also should be the same state preferentially, realistically, unless we're signaling there's some sort of um, sublimation happening, or a change of state between the reactions, which we're not getting into here. With oh, it's actually solid. Yeah. No, it's a gas. So this was wrong. All right. Sorry about that. All right. So both of these will each cancel out. And now I have O2 on this side, and I also have O2 on the same side. Now, but we don't care. We know now everything is in the right place. So that means these O2s will have to add up. And if I have 2 and a 1, I'll have, well, 2 plus 1 is 3. So if they're on the same side, you add them. If they're opposite sides, you delete them. But the way you decide to make them the right way is by putting them, um, based on what you want your products to be and what you want your reactant to be, and you'll be signaled that from the pieces that offered to you in the question. Now, so you flip sides when you flip around. You when you time anything, coefficients change them. You also time that factor by your enthalpy change per piece. All right, now we're almost done. Let me show you why we're almost done here. If I put all these pieces together, I will in fact have myself the same reaction that's in question. That means I did my work correctly and everything is in place. When I could get this back from the little pieces, that means, and I apply all the changes that will correspond to such changes I made to get my equation in question, I will be able to combine all my values. When I say combine, that means sum them all up. And if they're negative, I'll just say 198 plus a negative 594, and you get the idea here. I'll add these up together, and eventually I'll get the answer of 792. Now, if we look and check the teacher's work, that's correct. That's good. That means um, we get confirmation from the problem itself that we did it correctly. Now, this is all this saying is when I go in this reaction from this point to the end point, I will get this enthalpy change. So this would represent this number, this value of the delta H of the reaction itself. I hope that helps, and it always helps to kind of set everything straight. Make sure you have your right reactants on the left, and another equation will have the right products on the right. And then eventually, when you do that, you will see things that you can cancel out, things that are on the same side and that are similar state and similar everything will get added up together, and well, the rest just kind of falls in place. And as you see, we got what we're looking for. Every time you multiply an equation by a factor, that factor will also multiply by its enthalpy. When you switch the reaction backwards, um, you will also switch the sign of your enthalpy change. I hope this video helped, and we'll see you in the later one.